Hi, we're looking at significant figures today. This is a very important method in dealing with approximate data, which is really all real-world measurements are going to be approximate. So in this example here, we have your home. Okay, so this is where you live. This is your bicycle. Here's a school, and here's a little restaurant over there. And I've kindly placed a little ruler or measuring device over here, measuring the distance. So over here would be 700 meters away from your home. We want to just measure the distance to each of these different locations from your home, right? So let's take a look at the first one. We want to find the distance to the bicycle from your home. Okay, so what would you say that is? Well, if you look over here, we can kind of see it's going to be around over here. This is where the bicycle is located, so that's less than 100, and we can count, here's 50, 60, 70, so it's between 70 and 80 meters. We can sort of estimate that it looks like it's about halfway between 70 and 80 meters, so we're going to say that's 75 meters away from your home. Okay, so using analog measuring devices like this ruler, you can often estimate sort of one digit beyond the smallest actual gradation here. So each of these gaps here represents 10 meters, but we can kind of see in between there, right? So we can estimate a little bit beyond the tenths place and into the ones place here. That's what we're talking about. So when we talk about significant figures, we look at this number, 75 meters, and we say that there are two significant figures here, okay? It's two significant figures. And we say it's two because literally you can count there are two digits and each of them is meaningful. Each of them is significant, contains information that we measured, right? So two sig figs we'll say we're going to have over here. Now, if I was to take this number, 75 meters, and convert it into kilometers, what would I get? Well, I would get 0.075 kilometers. Okay, so now I'm measuring this in kilometers. How many significant figures do I have? Well, it's the same measurement, right? I haven't changed how I measure it. I'm using the same ruler, so it can't be any better or any worse. I still have exactly two significant figures, okay? Just like before, that doesn't change. These zeros, these leading zeros that come before the actual significant figures are not significant, right? They're not very meaningful. They're just here sort of as placeholders so that I can have the correct order of magnitude here when I'm talking about kilometers. Because really any number has an infinite number of leading zeros in it anyway, right? They don't really carry any meaning, so we don't count them as sig figs. Okay, so basically one of our first important rules that we're going to find here is that leading zeros are not significant. Okay, that's the first important rule here about sig figs we want to discover when just converting here. Okay, what else do we know? Well, let's measure the distance now to your school. Okay, let's do that. So the school, your neighborhood school here, looks like it is going to be more than 300, but less than 310. And if I look at this, I can kind of squint. It's more than halfway between. So let's say that's 307 meters. Okay, that's more than 300, less than 310, and more than halfway over to 310. Right. So 307, I think, is a reasonable number. How many significant figures would you say we have here? Well, we measured this 300, that's pretty clear. We measured that it's between 300 and 310, that's good. We estimate this 7, so that's okay. We have three significant figures here, okay? So this 0 in between here is meaningful. It has significance, so we are going to count that because that is telling us that it's between 300 and 310, and that's true. That's what we're measuring. So we measured that 0, okay? So this is telling us that when you have zeros in between other numbers, internal zeros, those are going to be significant, okay? So that's another important rule that we can see just by taking a simple distance measurement here. Finally, let's take a look at the distance to the restaurant, okay, to the food house. How far away is that going to be? Well, we can see it's pretty much smack on to this 600 meter line right there. It's not even just a little bit to the left or to the right. So I'm going to say that this is 600 meters away, okay? And now here, How many significant figures do I have? Well, this 6, I clearly measured that, right? It's here. And this is correct, right? It's not 310, it's not 590, it's 60. And then this to the last estimated digit there, that's also significant because I can see it's not, I can't measure, 1 meter to the left or the right. It looks like it's right there. So I'm going to say that right here I have 3 significant figures, and I do. But what if I was to transform this into centimeters? Okay, I want to convert this now into centimeters. What would this look like? Well, there's 100 centimeters per meter, so I'd have to try and take this and have to multiply by 100, right? So this is going to give me 60,000 centimeters. Okay, 60,000 centimeters, the same as 600 meters. How many significant figures do I have here? It's the same measurement, can't be any different, so I must have 3 significant figures, right? But that's these numbers here, but it's confusing, right? How do I know that these zeros here are significant, but these are not, right? How do I see that? And in fact, over here, how do I know that these zeros are significant at all? It's not clear, okay? So this is the problem with trailing zeros. Trailing zeros are ambiguous. It is not clear if they are significant or not. How can we try and fix this? Well, in an ideal world, we would invent a new symbol that we could use here. So we wouldn't write down zeros that are not significant. You would write down some placeholder symbol, because that's really what these zeros are doing. These zeros here are not true zeros. We don't know what they are. We never measured using this ruler down to the individual centimeter. So these zeros are just placeholders that have to be there so that we can represent the sort of the size, the order of magnitude here correctly. These are place value placeholders, right? Not actual zeros. But in the real world, we don't typically use placeholder symbols. We just write down zeros. And so what we can do is, if you have a situation like this where everything is significant to the very end, what you can do is you can write down a decimal point right here. So if you have a number that ends in a decimal point, that decimal point indicates that all of the numbers to the left are significant, including these zeros. That's one way we can do this. Not a super common technique, but we can. But what if we wanted to have this number written in centimeters, right? Not in meters. Well, in that case, we will use scientific notation. That's what we learned about in our previous class. So I would write this as 6.00 times 10 to the, looks like we have 4 centimeters. And now in scientific notation, all of the zeros here are significant because all zeros to the right of a decimal point that you write down are going to be significant. Otherwise, why would you write it down? If you didn't make that measurement, you wouldn't write it down, right? So trailing zeros can be ambiguous, but if you've got a decimal point, then any trailing zeros after that decimal point are significant. And so now here it is clear that we have 3 sig figs. Okay, so these are just some rules dealing with how zeros work in significant figures. And it's just unfortunate that sometimes we use zeros as a placeholder symbol instead of actually the value 0. But that's what we got. Let's look at how we can add and subtract zeros now. Add and subtract numbers. So here we've got a little rectangle, and we want to find the perimeter of this rectangle. That's the task, okay? And we've got 2 different rulers. We've got one here that's a little more coarse and one here that's a little more fine, okay? Let's say these are measuring things in terms of centimeters, okay? So these are centimeter rulers. So let me first try and measure sort of the length here, okay? I want to try and measure the length here of that rectangle. And because this is a more coarse gradation here, I have to estimate. So this is, less than 4.5. I'd say maybe that's around 4.3. Let's say about 4.3 centimeters. Okay, so let's say that is the length. And then I'm going to estimate this width over here. Well, it looks like it's a little bit less than 2. So maybe 1.9, and I'll estimate 1.98 centimeters. Okay, so I can go a little bit further. Now notice when I have finer gradations, I can estimate to a greater degree of precision here, right? So I can have, essentially what I've got here is I've got 3 sig figs, and on this measurement I only have 2 sig figs because my measuring device is not as good when I was measuring the length. And that's what the number of significant figures is really about. It's about how good did you make that measurement. More sig figs mean you have a much finer measurement, right? Fewer sig figs, if you only had 1, that's a very rough estimate, right? So how do we find the perimeter? Well, we're just going to have to add the length plus the width plus the length plus the width. Okay, so let's do that. So let's see what, if I was to add both of these lengths together, what would I get? So I would get 4.3 plus 4.3. This would give me 6. This would give me 8.6 centimeters so far. And then on this side, I would have, let's do 1.98 plus 1.98, right? Let me add these together, get a 16. Here I'm going to get a 19, and here I'm going to get a 3.96 centimeters. Okay, so that's going to be the width plus the width. This is the length times plus the length. Now I have to add these together. So let's do 8.6, and then we've got a 3.96 that we're going to add together here. Let's see what we get. Okay, so here there's nothing above me, so I'll just have a 6. This is 9 plus 6, that's a 15. And this is going to be a 12. This is going to be a 12, right? Okay, so 12.56 centimeters. So this is what I am getting for my perimeter. But there's a problem. The problem is that I am pretending that this number here is a 0. I just added 0 plus 6, but it's not a 0. I don't know what this is. This is some placeholder value that I was unable to measure because it's from this very coarse ruler right here. And I estimated it was 4.3, but there's no way if I can tell it's actually 4.28 or 4.32. It's not possible to know that with this ruler. And so I cannot include this hundredths place in my final answer for the perimeter because it's based on assuming this is a 0 when I know it's not. Well, probably not a 0. It could be anything, right? And so what I'm going to have to do is I'm going to have to round this number. 12.6 centimeters. Okay, so here we go. I've rounded it off. And now I can say with some degree of confidence that this is a good number I can work with. Okay, so this number here is going to be what I use for my perimeter. So the idea is when I have bad measurements and good measurements, I have to round my final answer off to match the degree of precision of my worst measurement, right? Sort of the decimal place is going to be important here. Here I don't know what this is, so I can't have this degree of precision inside my final answer. It's just not reasonable, right? I don't know what that is. So for addition and subtraction, you're going to look at the actual decimal place that you have for your worst measurement, and that is as good as you get for your final calculation. Let's take a look at multiplication and division, right? So that one also works for subtraction. We're going to look now at finding the area of this rectangle, and this rule is also going to work for division. So once again, we're going to have the same length and width as we had before. So we said that this was a width of 1.98 centimeters and a length, we said, of 4.3 centimeters. So to find the area, we're going to have to multiply these together. Okay, so if we multiply these together, what do we get? Well, let's see. We're going to have 1.98 multiplied by 4.3. And that's going to give us 8.514. Okay, there we are, 8.514, and that's square centimeters, right? That's the units here that we have. Now that's pretty precise, isn't it, right? Down to the hundredths to the thousandths place here. Is that reasonable? Is it reasonable for us to claim the area is 8.514 when we're not super sure about this 8 and we're not super sure about this 3, right? It's probably around there, but, you know, plus or minus, right? So it turns out, no, it's not reasonable for us to give an answer that is so precise. In fact, we can sort of imagine that this measurement here is actually expressing a range of measurements. We can sort of imagine that what we're talking about here is not 4.3 exactly, but somewhere between, say, 4.1 and, 4.2 and 4.4, right? So we're sort of estimating plus or minus 0.1. And that's reasonable, right? This is about halfway. This is sort of between in there, in that range, 4.2 to 4.4. And this 1.98, similarly, is also an estimate, right? We don't know it's exactly 1.98. Maybe it's, I don't know, maybe it's 1.97. Maybe it's 1.99, somewhere in there. I think probably it's closer to 1.98, but this is sort of a range. That's what approximate numbers are actually implying, a range of values. So let's find what the area would be if we assume that these ranges were correct. Okay, so if we on the low end, we get sort of a minimum possible area, and on the high end, we get a maximum possible area. Let's see what we get there. Okay, so 1.97. 1.97 multiplied by 4.2, we're going to get 8.274. So we get our 8.274, and on the high end, we're going to have a 1.99 times a 4.4, 8.756. 8.756 square centimeters. And so what we have here is a range of possible values where what we estimate to be correct is sort of in the middle, between the low and the high end, right? So when we look at it that way, we're going to see that actually this last number here is not really significant at all, because it could be anything, right? It could be anything from 0 to 9. And same thing with this one, because this one could be 0 to 9. Really, our estimate is only going to be good up to this 5. This 5, it could be a 5, maybe it could be a 4 or a 3, or it could be a 6 or maybe a 7, but it can't be an 8, it can't be a 9, it's not going to be a 0, right? So this 5, although it's not an exact measurement, because we started out with not exact measurements, we don't know if this is really an 8, right? It could be a 9, it could be a 7. So we're not exactly super sure on this 5, but it does have meaning. It is meaningful, it is significant. This digit can't be just anything. It's probably close to a 5. So we're going to round this number off, and we're going to say it's just 8.5 square centimeters. Okay, we round that off, and so what we're left with is a number here with only 2 significant figures. And when we started, we had a number here with 3 sig figs and a number with 2 sig figs. So sort of the rule of thumb here, the general rule on multiplying and dividing numbers is our final answer here is going to have the same number of significant figures as the fewest sig figs you had in the input numbers, right? So here the fewest sig figs we had was 2, okay? So we're going to round our final answer so that it has the same number of significant figures as the measurement with the least number of significant figures that we're starting with. That's how we do multiplication and division. You could also imagine if you're doing like, squares, right? If you took this 4.3 and you squared it, your final answer, squaring is just repeated multiplication. So you start with 2 sig figs, you have to end with 2 sig figs, right? Same thing if you're doing a square root of 4.3, you'd want to round that off so you only have 2 sig figs in your final answer. If you're doing the maybe the square root of 1.98, well, then your final answer should have 3 sig figs, right? So you round it off. Roots and exponents, these are essentially repeated multiplications or divisions. So there we go. Okay, so this is a brief introduction to significant figures and the rules that we use with them. We looked at multiplication and division, as well as addition and subtraction, and we also looked at how zeros work in significant figures and what they actually mean. Come back for our next lesson where we're going to practice using calculations with significant figures and scientific notation. Okay, I'll see you there.